Hello friends, welcome to my new video on action potential. So let us start about the discussion of action potential. So we have already discussed about the properties of the excitable tissues like conductivity, infatigability, accommodation, refractory period and all or non-low. And in this lecture we will discuss about the excitability of nerve and muscle fiber. So first of all, what is the excitability? Excitability means the physiochemical change that occurs in a tissue when the stimulus is applied to excitable tissues like muscle and nerve. And stimulus is defined as an external agent which produces excitability in the tissues. And there are different types of the stimulus like mechanical, thermal, chemical or electrical. And in experimental studies, we use electrical stimulus. Why? Because its strength and frequency can be accurately controlled. And which type of the stimulus is used in experimental study? Why? This is a very frequently asked questions in Viva. So usually electrical stimulus is used in different experimental study because it can be easily quantified. Strength and duration of the stimulus can be controlled and it causes least damage to the tissue, and phenomena of the excitation and impulse propagation are themselves electrical in nature. Then second question is like that which is the type of current used for stimulating the excitable tissue and why? So Faradic current is used for the purpose of the stimulation because it is a short-lived and so that causes a very little damage to the tissue. And galvanic current on the other hand, it is a continuous current and which causes damage to the tissue. Then there are a certain definition of various stimulus like a subminimal stimulus or subthreshold stimulus. So subthreshold stimulus is the stimulus that does not evoke a response, and a threshold stimulus is the minimum strength of the stimulus that is just sufficient to evoke a response, and this is also known as minimal or liminal stimulus. A maximal stimulus that produces maximum response, and supramaximal stimulus is stronger than the maximal stimulus but does not change the magnitude of the contraction after reaching a peak. Then response due to stimulation of the nerve fiber. So when the nerve fiber is stimulated based on strength of the stimulus, two types of the response are developed. First is action potential or nerve impulse. So action potential develops in a nerve fiber when it is stimulated by a stimulus with adequate strength. If we applied a stimulus with not adequate strength, then the nerve fiber or muscle fibers are not stimulated and there is no development of action potential. So it is necessary when we give the stimulus but with adequate strength, then the excitable tissue give a response. Adequate strength of the stimulus that is necessary for producing the action potential in a nerve fiber that is known as threshold or minimal stimulus, and action potential is propagated. Then second response is local potential. So now when the stimulus with the subminimal strength is applied, only electronic potential develops and the action potential does not develop, and electronic potential is non-propagated. Action potential is propagated but the local potential is not propagated. Then cat electronic and unelectronic potential. So while recording the electric potential in a nerve fiber, two electrodes, namely the cathode and anode, are used, and the potential change that is produced at cathode that is known as cath electronic potential, and the potential that is developed at the anode that is known as unelectronic potential, and only the cath electronic potential can be transformed into the electronic potential or action potential. Now we discuss about the action potential or nerve impulse. So action potential in a nerve fiber is similar to that in a muscle except for some minor differences. So what are the differences between the potential in nerve fiber and muscle fiber? So resting membrane potential in nerve fiber, that is about minus 70 millivolt, and in skeletal muscle fiber which is about minus 90 millivolt, and firing level in a nerve fiber that is about minus 55 millivolt, and in skeletal muscle fiber which is about minus 75 millivolt, and the end of depolarization in nerve fiber which is about plus 35 millivolt, and in skeletal muscle fiber which is about plus 55 millivolt. So these are a different cell types, and in which what is the resting membrane potential and what is the value of the resting potential in different types of the cell type. So first of all, neuron, in which the resting membrane potential that is about minus 60 to minus 70 millivolt. In skeletal muscle that is about minus 85 to minus 95 millivolt. In smooth muscle minus 50 to minus 60 millivolt. In cardiac muscle minus 80 to minus 90 millivolt. In hair or cochlea and minus 55 minus 15 to minus 40 millivolt, and in astrocytes resting membrane potential which is about minus 80 to minus 90 millivolt, in erythrocytes minus 8 to minus 12 millivolt, in photoreceptors minus 40, in dark light to minus 70 in light. So this is the resting membrane potential in different cell types. Now we discuss about the axon potential curve. So resting membrane potential in the nerve fiber that is about minus 70 millivolt, and the firing level which is about minus 55 millivolt. This is the firing level and this is about minus 55 millivolt, and the depolarization that ends at plus 35 millivolt. And usually the axon potential starts in the initial segment of the nerve fiber. So this is a axon potential curve, and this is the stimulus artifact, and this one is a latent period, and the firing level starts here, and this is a overshoot isoelectric line, and this one is a rapid depolarization and rapid repolarization, that is known as spike potential, and then this is a repolarization. This one is a after depolarization and this one is after hyperpolarization. Then it comes back to resting membrane potential level. So first of all, what is the definition of the axon potential? So axon potential is defined as a series of the electrical changes that occur in the membrane potential when the muscle or nerve is stimulated, and it occurs mainly in two phases, depolarization and repolarization. Then what is the depolarization? So depolarization is the initial phase of the axon potential in which the inside of the muscle becomes positive and outside becomes negative. So that is the polarized state, means resting membrane potential is abolished and resulting in depolarization. In the resting membrane potential, inside of the membrane there is a negative and outside there is a positive. But when we give the stimulus, then occurs a depolarization, means reverse of the resting membrane potential. So inside becomes positive and outside becomes negative. Then repolarization. Repolarization is the phase of the axon potential in which the muscle reverses back to the resting membrane potential, and that is within a short time after the depolarization. The inside of the muscle becomes negative and outside becomes positive. So the polarized state of the muscle is re-established. Then axon potential curve. So axon potential curve, that is a graphical registration or recording of the electrical activity that occurs in a excitable tissue such as muscle or nerve. After stimulation, it shows the three major parts: latent period, depolarization and repolarization. So resting membrane potential in the skeletal muscle that is about minus 90 millivolt, and in the nerve fiber which is about minus 70 millivolt, and it is recorded as a straight baseline. Then axon potential in a skeletal muscle. Here A, this one A, that is it is the point where the opening of the few sodium channel, not all the sodium channels are open, but when we give the stimulus, only a few sodium channels are open. Then at the point B, means here, Here be the opening, this is a firing level, and here opening of many sodium channel, and see here there is a now starting of the closing of the sodium channel and opening of potassium channel. Starts opening of the potassium channel and there is a totally closure of the sodium channel and starting of opening of potassium channel at the C point, and at the D point here the closure of potassium channel. So these are the several points that indicates the opening and closing of potassium channels. Now latent period. So latent period, it is the period when no change occurs in electrical potential immediately after applying the stimulus, and it is a very short period with the duration of zero point 0.5 to 1 millisecond, and this one is a latent period. Okay, this one is a latent period and its duration which is about 0 point 0.5 to 1 millisecond. Then stimulus artifact. So here this is a stimulus artifact. So when the stimulus is applied, there is a slight irregular deflection. You can see here there is a slight irregular deflection is seen. So there is a slight irregular deflection of the baseline for a very short period, and that is known as stimulus artifact. And the artifact occurs because of the disturbance in the muscle due to leakage of the current from the stimulating electrode to the recording electrode. And this stimulus artifact that is followed by latent period. So this is a stimulus artifact and that is followed by latent period. Then depolarization. So depolarization starts after the latent period. Initially it is a very slow. Initially it is a very slow and the muscle is depolarized for about 15 millivolt. Then comes to firing level and depolarization. So after the initial slow depolarization up to 15 millivolt, the rate of the depolarization increases suddenly, and the point at which the depolarization increases. So here at the firing level, almost all the sodium channels are open, and that is known as firing level. Then overshoot. So this one, that is a overshoot. So from the firing level, the curve reaches the isoelectric potential or zero potential level. And it occurs very rapidly and then shoots up beyond the zero potential, means isoelectric base, up to plus 55 millivolt, up to here plus 55 millivolt, and that is known as overshoot. That is known as overshoot. Then repolarization. So when the depolarization is completed at plus 55 millivolt, the repolarization starts. And initially the repolarization which is occurs very fast and then it becomes very slow. Then rapid rise in the depolarization and rapid fall in the repolarization are together known as spike potential. And it lasts for about 0.4 millisecond. Okay. Now after depolarization or negative after potential. So this one after depolarization or negative after potential. So rapid fall in repolarization. This one is a rapid fall in the repolarization that is followed by a slow repolarization. The process becomes very slow and that is known as after depolarization or negative after potential, and its duration that is about 2 to 4 milliseconds. Then after hyperpolarization or positive after potential. So after reaching the resting level minus 90 millivolt, here minus 90 millivolt, it becomes more negative. It becomes more negative beyond the resting level. This one is a resting level, and here after reaching the resting state it becomes more negative beyond the resting level, and this is known as after hyperpolarization or positive after potential, and it lasts for more than 50 milliseconds, and after this the normal resting membrane potential is restored very slowly. So we have already discussed about the action potential curve. Now we discuss about the ionic basis of the action potential. Role of the voltage gated sodium potassium channels. Now the development of the action potential was studied by Hodgkin and Huxley using the voltage clamp technique. According to Hodgkin and Huxley theory, the sequence of the events is like that: polarization phase, depolarization phase, repolarization phase, after depolarization and after hyperpolarization. Now polarization phase or resting membrane potential. So resting membrane potential minus 70 millivolt, that is due to distribution of the more cations outside the cell membrane and more anion inside the cell membrane. And at this point, though the sodium is more in the extracellular fluid, it cannot enter the cell due to impermeability of the membrane. Then depolarization phase. When the threshold stimulus is applied to the cell membrane, at the point of stimulation, the permeability of the membrane for the sodium ion increases. At first, the rise of the permeability for the sodium is slow and then it reaches the firing level. Now, when the membrane potential that depolarizes, the sodium channel starts opening up. Now, the opening of the sodium channel depolarizes the membrane further, and that leads to the opening of the greater number of the sodium channel, and thus there is a positive feedback spiral and so-called Hodgkin cycle that resulting in a rapid change in the membrane potential. So this is a Hodgkin cycles. At first there is a opening of the sodium channel, few number of the opening of the sodium channel, and then there is a membrane depolarization, then opening of the sodium channel, few more opening of sodium channel, then more membrane depolarization. So this cycle goes again and again, and then more number of the sodium channels are open, and this is a feedback spiral, and that is known as Hodgkin cycle, that results in a rapid change in the membrane potential, and that is also known as positive feedback spiral or Hodgkin cycle. Once the firing level is reached, the voltage gated sodium channel open massively, and as the concentration gradient and electrical gradient of these ions are directed inwards, and there occurs a rapid influx of the sodium ion into the cell as seen in a figure. Then rapid entry of the sodium is sufficient to overwhelm the repolarizing forces, and the membrane potential seems to be carried towards the equilibrium potential of the sodium plus 60 millivolt. So during depolarization phase, the sodium channels open and potassium channels remain closed, and sodium channel remains open during depolarization phase. However, the depolarization does not reach a value greater than 30 plus 35 millivolt because of following reasons. The sodium channels are inactivated in a fraction of the millisecond and the gates close again. And due to rapid influx of the sodium, the concentration gradient diminishes. And during the overshoot phase, the electrical gradient for the sodium also reverses. It is a short acting channel. So it opens and closes very fast. Now change in the membrane potential during the depolarization that results in opening of the voltage gated potassium channel. Therefore, within a fraction of the millisecond of the threshold excitation, the potassium leaves the cell along its concentration gradient. Then comes to repolarization phase. So repolarization that occurs due to decrease in further sodium influx and potassium efflux through the voltage gated potassium channel, which open later than sodium channel but remain activated for a prolonged period. So as seen in figure, here the potassium channels open up, and that results in a rapid efflux of the potassium ion, and sodium influx decreases. So decrease in the sodium influx and efflux of the potassium that causes a net transfer of the positive charge out of the cell that serves to complete the repolarization. Now after depolarization, so after the rapid initial repolarization, further repolarization occurs very slowly, and this is due to the fact that the rate of the potassium efflux slows down as the electrical gradient responsible for the initial rapid diffusion declines, and this last phase of the slow repolarization, that is due to slow efflux of the potassium, and that is known as after depolarization. So here during the after depolarization and hyperpolarization phase, the sodium channel that gets closed and potassium efflux slows down. Then after hyperpolarization, the slow efflux of the potassium continues even after the resting membrane potential is reached, and that results in a prolonged phase of the hyperpolarization during which the membrane potential falls up to -72 millivolt. However, a little after, the voltage gated potassium channel also closed or shut down. The final ionic distribution is brought to the resting state by the action of the sodium potassium pump and leak channels. So here during the after depolarization and hyperpolarization phase, the sodium channel gets closed and potassium efflux slows down, and this is a restoration of the resting membrane potential. Then what is the role of the calcium ion? So in addition to sodium and potassium ions, the calcium ions also plays some important role in the development of the action potential. The concentration of the calcium in the intracellular fluid is very low as compared to extracellular fluid. Therefore, when the sodium channels are open, some calcium ions are also moved inside the cell through this open sodium channel. Further, a separate class of the channels are also known as slow calcium channel that also exist in the cell membrane, and these calcium channels also open up admitting a calcium during the development of the action potential. These calcium channels are especially important in cardiac and smooth muscles where these are in more in number. In fact, in some types of the smooth muscles, the fast sodium channels are hardly present. So the action potential then are caused almost entirely by the activation of the slow calcium channels. And very important note is that low extracellular calcium concentration that increases the excitability of the nerve and muscle by decreasing the amount of the depolarization necessary for initiating the changes in the sodium and potassium conductance that is required for the action potential, and increasing the calcium concentration that stabilize the membrane by decreasing the excitability. So now in regarding these lectures, if there is any questions, please write down in comment section and give me a feedback. And thank you for listening and attention. Thank you again.